Hey guys, what's up people? Welcome to the session. I hope all of you guys are doing good, taking care of yourselves and staying safe. And once again, I wish you guys all the very best of luck for your term one results. I'm pretty sure it's going to come out in the next couple of days. So good luck for that. I hope you guys are, kind of excited. I know some of you guys are tensed about it. Most of you guys are tensed about it. But I would just say this, there's nothing that you can do to control it. So just relax yourself and focus on your term two syllabus at this point of time, because that is going to yield you the right result, rather than just thinking about it and worrying about what your term one exam is going to be like, right? So in order to help you with your preparations, people, we are back with another video, another one shot series. So today we'll be starting off with electricity. Unfortunately, it's given a sound. No, we have done the last session was on sound, which came out yesterday. So today we'll be coming out, we're back with another video of one shot series of current electricity. So these are the topics that we'll be having in this. These are the topics that you have in this chapter. We have current and potential difference, Ohm's law and resistance, what is EMF, terminal voltage, and internal resistance. Then we also have combination of resistors, series and parallel. We also have electric energy and electric power, and then finally heating effect of electric current. Now honestly people, the thing is that if you guys want more more help with current electricity, I have done a lot of videos of this on for CBSE students, and it's actually very similar to that of CBSE. So if you guys want extra help, you can always refer to those electricity videos of CBSE. That is definitely going to help you with those topics. Most of the topics you have is, except for EMF, terminal voltage, and internal resistance, everything else is there in the CBSE videos also. So if you guys want to check that out, you can check that out as well to help you with your preparations. It's definitely going to help you with your preparation for current electricity. Right guys, so without wasting much more time, let's get into the topic. So what we're going to do in today's session is basically learn about these three topics. We're going to focus on current electricity. What is current, what is potential difference, what is Ohm's law, what is resistance, and what is EMF, terminal voltage, and internal resistance. So these are the topics that we're going to be learning today. So without wasting much more time, let's get into the topic. So here is current and potential difference. So what is current and potential difference? See guys, current is a very common term. Like for example, when the power goes off, generally even at my home, as soon as the power goes off, all of us synonymously will be current poi, because we speak Malayalam at home, like current poi, in the sense current is gone. Or probably in your home also they say the same thing, or maybe light chali gayi, something like that, right? Now why do we call it as current? Now when you think about current, is it something which is only related to electricity, or is it something different altogether? So please listen carefully guys. Current is actually a very generic term. Current means flow of something. So current is not something which is only related to electricity. Current is a very generic term, a generic English term. For example, if water is flowing, that is called as water current. If air is flowing, that is called as air current. So depending flow of anything is what is called as current. So here when you talk about electricity or electric current, it is nothing but the flow of electric charges. So when these electric charges are flowing through a conductor, that is what is defined as current. The flow of charge, the flow of electric charge is what is known as electric current. Now the fact is guys, you have experienced current in a lot of different ways. So let me explain what electric charge is. Alright, let me explain what is an electric charge so that you understand this definition of current. So here is the thing guys, I don't know if you ever tried this before. So basically when I was a kid, I used to do this all the time. So what I used to do is I used to take a scale and rub it on my head, and then take couple of pieces of paper. Whenever I'm bored, I used to take a piece of paper, tear it into small pieces, and try to attract these paper near it. I used to feel like some sort of a magician at that time. Now, I'm pretty sure you'd have already done this, like you've done this at least once in your life. Now why does this happen? The reason why this happens is because when you take the scale and rub it on your head, the scale gets charged. And because of the charge that the scale has, it attracts the paper that is lying on the table. So what is in charge is nothing but it's the fundamental property of a material. It is a fundamental property of a material which either helps in attraction or in repulsion. So like charges like positive and positive charge, or negative and negative charge, will repel each other. Positive and Negative, on the other hand, will attract. Positive and positive, negative and negative will repel, but positive and negative will attract each other. This attraction or repulsion is actually decided, or we get to know about this attraction or repulsion using these charges. Now, if I have a conductor, imagine this is a conductor, right? And I want to know how many charge is present on this conductor. That is, generally when you talk about charge, we are referring to electrons. So let's say that I want to find out the number of electrons in this conductor, because if you talk about if you talk about this particular, let's say a copper wire, right? Now, a copper wire is made up of atoms, right? We all know that it's made up of atoms. So you have copper atoms which are arranged in a certain format to make up a copper wire. Now the thing is, guys, in an atom, if you remember, you have electrons, protons, and neutrons. The fact is, neutrons and protons are present inside the nucleus. They're both present inside the nucleus. And electrons are basically revolving around the nucleus. So getting a neutron out or getting a proton out is very, very difficult. Taking out a proton is very, very difficult because you have to spend a lot of energy. But electrons, on the other hand, can be easily taken out from their valence shell, and they are basically what is called as free electrons. I'm pretty sure you've already studied this in your chemistry. So if I have a conductor and I want to know how many charge is present on this conductor, the formula is, guys, Q is equal to Ne, where Q is nothing but the charge, N is the number of electrons, and E is the charge of an electron. So number of electrons you can find out by using a very simple formula. So if you want to find out the number of electrons, you need to know the mass of the object, you need to know the atomic mass of the object, and you also have to multiply that with the Avogadro's number. I'm pretty sure you remember that also. Avogadro's number is like 6.022 into 10 to the power of 22, if I'm not wrong. So that is basically the number of atoms. So you can actually find out the approximate number of electrons using that formula, and E is nothing but the charge of an electron. So charge of an electron, as you guys know, it's nothing but 1.6 into 10 to the power of minus 19 coulomb. So this is the charge of an electron. So number of electrons into the charge of an electron will give you the number of charges present in a conductor. So for example, if I take this as a conductor, the number of electrons can be discovered or found out by using this formula, Q is equal to Ne. As simple as that. All right. So, but yeah, now the rate of flow of this charge is what is called as current. Rate of flow of this charge is what is called as current. So if you talk about the mathematical expression to express current is represented by the letter I. So I is equal to Q by T is the formula. Now the formula can also be modified to I is equal to Ne by T, because Q is equal to Ne. So you can also substitute as Ne by T, where Q is the charge and T is the time taken. So Q is the flow of charge that is going through if I take a certain point on the conductor, Q is nothing but the number of charges flowing through that point, and T is nothing but the time for which the charge is flowing through that point. So this is what is current. But again, guys, what causes the current to flow? Just think about it. If I have a conductor, what makes this current to flow from one point to another? This is where potential difference or electric potential comes into the picture. So what is this potential difference? What is this potential difference? Let's take a simple example. Imagine I have a plate. All right, and this plate is full of positive charges. You can see that it has a lot of positive charges on this plate. I have one positive charge which is at infinity. All right, at infinity, which means that it's so very far away. It's really, really far away that since this is also positive charge, this is also positive charge, there'll be a force of repulsion, right? Because positive and positive will repel. But imagine that this test charge that is there, this one unit charge that I have, is so far away that the force of repulsion is not at all felt. The force of repulsion is not at all felt. It is that far away that the force of repulsion is not felt at all. It's like this. Imagine I have two magnets. All right, there's one big magnet and there's another smaller magnet. Now, if I keep the small magnet far enough, there'll be no force of repulsion or attraction between these two magnets. So in the same way here also, I'm keeping this unit charge or this test charge far enough such a way that there's no force of repulsion at all. So that charge, I'm going to call it as the unit charge or the test charge. Let's say that I want to bring this charge from infinity to a point. All right, I want to bring it from infinity to a point. Now, when I'm moving this charge, obviously I have to do some work here. I have to spend some energy, I have to do some work to move it from one point to another. And this work done that I'm doing has to be against the repulsive force, because these positive charges are trying to repel this positive charge, isn't it? They're trying to repel this unit charge. So I have to go against the repulsive force and bring it from one point to another. This work done to bring a unit charge from infinity to a point, that is what is called as electric potential. This is what is called as electric potential. So potential or electric potential is nothing but the work done to bring a unit charge from infinity to a point, from some points, from some very distant point, infinity to a point. That is what is called as electric charge. So that is what is called as potential, electric potential. Now, if let's say guys, if let's say there is let's say that there is there's a unit charge again, but this time again you have more, what to say, there's a plate full of positive charges, and there's another plate which has only 2 positive charges, and there's another one over here. So this is one scenario, this is case number 1, and let's say this is case number 2. Now here guys, in which case is the work done more? In which case do I have to do more work, the first one or the second one? Common sense would dictate that I have to do more work over here in the first one. Why? Because there are more number of positive charges. So the repulsive force felt by this unit charge will be comparatively higher in comparison to this one, because the number of the number of positive charge on this plate is lesser in the second scenario. So the work done would be lesser. So this difference in work done, so there's a clear difference between these two, right? Now, if I connect these two plates, what would happen is that guys, you can say that this is at a higher electric potential. Why? Because the work done over here is more. This is at higher electric potential. This one, on the other hand, you can say that it's at lower electric potential because the work done here is less. Now, you guys know what is electric potential. It is nothing but the work done to move it from one point to another, from infinity to a point. So, in the first case, work done is more. In the second case, the work done is less. Now, if I connect these two plates with a copper wire, let's say, what will happen is that the charge will start to flow from 1 to 2. This is what is called as potential difference. It is nothing but the work done to move a charge from one known point, from one point to another. You already know what is this point. You already know this point. It's not infinity. It's a certain fixed point. So from one fixed point, if you want to move it to another point, this work done is what is called as potential difference. So the difference between potential difference and electric potential is the work done to move it from infinity to a point. Potential difference is to move it from one point to another. The formula is very, very simple, guys. Potential difference or electric potential is both represented by the letter V, which basically is nothing but the electric potential or potential difference, which is equal to work done, which is represented by the letter W, divided by Q, where because it's nothing but work done on a unit charge, right? So it's work done by Q. So like I told you before, base potential difference is nothing but the work done to move it from one point to another, from one known point, from one point to another. So here you see this, from one known point to another, the work done to move it from one point to another, that is what is called as potential difference. So the formula again remains same. So you can say that one is at a higher potential, the other is at a lower potential. So this work done is what is called as potential difference. That is what is represented by V21. So you see this V1 minus V2. So you're finding out the potential difference. So you can say that one is at a higher potential, the other is at a lower potential, and current always flows from higher potential to lower potential. So generally people, positive terminal of a battery is considered to be at higher potential, positive terminal is considered to be at higher potential, and the negative terminal is considered to be at lower potential. So current will flow from higher potential to lower potential. Just like it's like wind, it's like heat. So wind also flows from high pressure to low pressure. Temperature flows from high temperature to low pressure. Water flows from high pressure to low pressure. In the same way, current also flows from higher potential to lower potential. The SI unit of potential difference, guys, is joules per coulomb, because if you look at the formula, it's nothing but W by Q. So W, SI unit of W, that is nothing but work done is joules, and SI unit of charge is nothing but coulomb. So joules per coulomb is the SI unit of potential difference, which is also written as volts. Basically, to honor Sir Alexander Volta, we have named it as volts. So joules per coulomb is also known as volts. So you can either write as joules per coulomb or you can write as volts. In most cases, you will write it as volts. So but yeah, it's not that you don't have to remember this at all. There's a probability that they might ask you, like in one of the exams, there was this question that which quantity has SI unit, which is joules per coulomb, and majority of them had forgotten it because you keep learning it as volts, and you forget that joules per coulomb is nothing but potential difference. difference. So remember both of them. All right. Now, if you're ever asked to define what is 1 volt, guys, very simple. So we know that potential difference is equal to work done by unit charge. SI unit of potential difference is V, whereas nothing but volts. SI unit of work done is joules. SI unit of charge is nothing but coulomb. All you have to do is put a 1 in front of all the three and define it in your own words. So potential difference is said to be 1 volts when 1 joule of work is done on to bring a charge of, or to move a charge of 1 coulomb, or the work done is set. Okay, when a work of 1 joule is done on a charge of 1 coulomb, that is what is called as potential difference. Or to bring 1 coulomb of charge from one point to another, that is what is called as potential difference. All right, people. So that is what is called as 1 volt. So basically, people, this is how you define 1 volt. Now another concept that so I hope you guys understood that what is current and potential difference. These are one of the most two basic concepts that you need to know in order to understand this chapter better. But not only that, people, we also have something called as Ohm's law. Now what is Ohm's law is nothing but a very simple theory which states that more is the potential difference, more is the current. So for example, people, imagine I have a circuit. Whatever, if you look at this over here, you see this. So I've kept the resistance constant. All right, you see this. I'll tell you what resistance is in a minute, but I just want you guys to look at this GIF right now. I want you guys to look at the voltage. You see this. As I increase the voltage, if let's just bring it back to normal. You see this, as I increase the voltage from 360 volt to 800 volts, you see that the current value is also increasing. So here the potential, okay, so you see this. So as you increase a volts to 220 volts, you can see that the current is also increasing. So basically what Ohm's law states is the relationship between potential difference and current. So Ohm's law states that potential difference applied across a conductor is directly proportional to the current flowing through the conductor, or current flowing through a conductor is directly proportional to the potential difference applied at the two ends. So more the potential difference, more the current. So for example, people, imagine you have a simple circuit, all right, a very simple circuit. So you have initially connected one battery which has a let's say a voltage of 1.5 volts. So the amount of current flowing through it will be comparatively lesser. All right, let's say the current flowing through it is around 3 amperes. To give you an example, let's say instead of one battery, I connect 2 batteries now. All right, I connect 2 cells. So basically it's a battery. So when I connect 2 batteries, now it's 1.5 plus 1.5. So what is the total potential difference? It's 3 volts. So the current value will increase to 6 amperes. So as I increase the potential difference, the current is also increasing. That is what I'm trying to say, right? So it's not that always it's going to be double of it. So here you can see that it's double of the potential difference. The current value is double of potential difference. It's not always the case, but this is just an example to help you understand this. So what is Ohm's law? It's nothing but the relationship between the current flowing through a circuit to that of a potential difference. It says that the current flowing through a circuit is directly proportional to the potential difference applied across the conductor. This is what is known as Ohm's law. The reason why it's called as Ohm's law is because the person who discovered this was Sir Ohm. If you had discovered this, the name would have been different, but unfortunately Ohm discovered it, so it's called as Ohm's law. As simple as that. Mathematically speaking, people, it is represented as V is directly proportional to I, where V is the potential difference, I is the current. So more is the potential difference, more is the current. In order to remove this proportionality sign, we came up with a constant which is called as R. So the formula then slightly gets modified to V is equal to I into R, where R is known as the proportionality constant, which is nothing but your resistance. Now we'll understand what resistance is, but this is a very, very important formula, guys. V is equal to IR. You will be having numericals based on it, so please note it down. I'm pretty sure you guys know this, I'm pretty sure you remember this, but nonetheless take it down and refer to it whenever you want to, right? So V is equal to IR is the basic formula for that. So basically it says that resistance, if you rearrange the equation, so we can also write as R is equal to V by I, which means that more is the resistance, less would be the current. So resistance and current are inversely proportional to each other. Higher the resistance, lesser the current flowing through the conductor. The SI unit of resistance, once again, is nothing but Ohm, because again, like I told you before, to honor Sir Ohm, it is called as Ohm. It is represented by the letter, Greek letter omega. All right, this is nothing but omega. So it is represented by omega. So resistance is numerically equal to the potential difference applied across the flow of current, and it's basically it's directly proportional to the potential. Here, mathematically speaking, it's equal to the potential difference and inversely proportional to the current. But see, one thing you need to understand is, guys, if I have a circuit, it's not that when I increase the voltage, the resistance will increase. All right, if I increase, it doesn't work like that. If I increase the voltage, the resistance does not increase. So resistance affects the current, but voltage does not really affect the resistance. Although in the formula it says that R is equal to V by I. In real world, this does not hold true. Why? Because when you increase the potential difference, it does not mean the resistance of the wire would actually increase. Now there is a small graph that you can actually use to represent this whole potential versus current graph, or voltage versus current graph. And this graph is very, very simple. This is called as a VI graph. So basically, guys, like I told you, as the potential difference increases, the current will increase. So you can actually, it's basically nothing but a linear curve. So this linear curve is a representation of how potential difference and current are related. So as the potential difference increases, the current will increase, and that is what is shown over here. On the y-axis you have voltage, on the x-axis you have current, and it's basically going to give you a straight linear curve, because more the potential difference, more the current. And if you find the slope of this curve, you can actually find out the resistance. So the slope of the curve will give you the resistance, and individually on the y-axis you have voltage, and on the x-axis you have current. So this is the graph. It's called as a VI graph, which is basically used to represent graphically how voltage and current are related. Now, one of the biggest problem with Ohm's law is, guys, Ohm's law has a lot of limitations. Like, see, Ohm's law, like I told you, for Ohm's law, what is it? It is nothing but voltage is directly proportional to current. And if you look at the formula, V is equal to IR is the formula. So that means that R is equal to V by I, which means that more is the resistance, lesser is the current. So the thing is, guys, Ohm's law is actually dependent on the temperature as well. So if the temperature increases, the resistance will increase. So if the resistance increases, Ohm's law does not hold true. I'll tell you more about it as we go ahead, but please remember this, guys. Ohm's law does not hold true if the temperature is not constant. If the temperature is varying, then the particles or the electrons will gain more charges, and because of that, Ohm's law does not really hold true. Any device that follows Ohm's law, that is called as an ohmic conductor. Anything that does not follow Ohm's law, that is called as a non-ohmic conductor. Now, here's the thing, guys. For all those who are wondering, sir, what exactly is resistance? Resistance is nothing but, people, it is nothing but the obstruction offered to the flow of current. So just look at this analogy. You have this water pump, which is, which is pumping the water throughout this entire pipe. You see this over here, the pipe's, radius is actually decreased. Because the radius of the pipe is decreased, the water is forced to move through a smaller diameter. So what is happening is that the speed at which the water is flowing is actually reduced because of this lesser diameter. So resistance is this. Resistance is nothing but the obstruction offered to the flow of current. When electrons are flowing through the conductor, when current is flowing through a conductor, the obstruction offered, that it's like you can think of it as like the traffic that you have, or imagine that you're in a road. All right, imagine you're in a very busy road and you have to go from one place to another. All right, you have to go from one place to another. You have to go from here to here. It's about 100 meters, let's say. Now imagine there are a lot of people in between. Now, if there are a lot of people, no matter how fast you're trying to go, what will happen is that you will collide with people. And when you collide, what will happen? Your speed would reduce. So resistance is exactly that. Resistance is nothing but the obstruction offered to the flow of current. And the cause of resistance, like I told you just now, it is nothing but the collision. See, guys, when electrons are moving through a conductor, electrons are not moving in a straight line. They are actually colliding with other ions and other electrons. And every time they collide, they are losing electrical energy. They're losing some energy. They're losing momentum. They're losing some velocity. So that is what is the cause of resistance. So more the number of collisions, higher the resistance. Lesser the number of collisions, lesser the resistance. And more the resistance, lesser would be the current. It's inversely proportional. So if I keep on increasing the resistance, the current value would decrease. If I keep on decreasing the resistance, then the current value would increase. Now there are few factors that resistance actually depend on. All right, if I have to, let's say, change the resistance of a conductor, there are few factors, there are few things that I can change or mess around with in order to make that happen. All right, people. So one sec. There are a few factors that it depends on. So the first factor that resistance depends on is nothing but the length of the conductor. More the length of the conductor, more will be the number of collisions. Like I told you before, so it's like this. Imagine that you're on a road. All right, I gave you this example. Now imagine you're in a very busy road. So there's this road in Bangalore called as the Avenue Road. Now thing about Avenue Road is that no matter which day of the month you go to, you can't even see the road. Like it's like this. Imagine that you're standing on the first floor of this, of a building on this on Avenue Road. You will not be able to see the road. All you would see is black heads walking here and there. And imagine that you're in a busy street like that. I'm pretty sure every state has one of those places where it's very very crowded, right? All the time will be always crowded. So imagine you're in one such place, right? Now there are lots of people in between. No matter how fast you're trying to go, because of the number of people that are there, what will happen is that you'll collide and your momentum would be lost. And every time you lose momentum, again you try to gain some speed, again you hit someone, again you lose momentum, again you gain some speed, again you hit someone, again you lose your momentum. So more the number of collisions, lesser your or more time it takes, and you can say that there is more resistance. So length of the conductor is one of the major factor that it depends on, because more the length, more would be the resistance. So instead of 100 meter, let's say I have to travel 200 meters and the crowd is exactly the same. It's exactly the same, but I have to travel 200 meters now. So it'll take more time, there'll be more number of collisions. So length of the conductor is one of the major factors that resistance depends on. More the length of the conductor, more the number of collisions. So that means that they'll take more time to reach from one point to another. So we can say that mathematically speaking, resistance is directly proportional to the length of the conductor. So it's directly proportional to L, which means that it's directly proportional to the length of the conductor. The second factor that resistance depends on is the area of cross section. So imagine guys, imagine the same avenue road, right? So you have so many number of people right now, all right? So many number of people standing on the roads. Now, if let's say the government decides to widen the road, now, if they widen the road, then you will not take that much time. You can easily navigate through the spaces and get from one place to another faster. So this is what is another factor that resistance depends on, which is nothing but the area of cross section. So if you have a wider wire, the resistance would be actually lesser. If you have a thin wire, on the other hand, the resistance is more, because the electrons are forced to move in a narrow space, which means that they are bound to collide and they'll have more number of collisions as well. But if you have a wider area, that means that the number of collisions would be less, because they can easily navigate through it and they can reach from one end to another. So mathematically speaking, people, you can say that resistance is inversely proportional to area. More the area, lesser the resistance, lesser the area, more the resistance. The last, but definitely not the least, the last factor that it depends on is the temperature of the conductor. More the temperature, more energy that these electrons would gain, and the more energy that these electrons gain, they'll start to move more randomly, which means that they'll collide more number of times, and hence the resistance will also increase. So temperature of the conductor is also one more factor that it depends on. But mathematically speaking, people, like I told you, resistance is directly proportional to L and resistance is inversely proportional to area. So you can write it as R is proportional to L by, simple, because on the left hand side you have resistance. Now once again, here also, to remove the proportionality sign, we introduce a constant called as resistivity. So the formula then gets modified to R is equal to rho into L by A, where rho is the resistivity. So what is resistivity? Is nothing but it is the property of the material to provide resistance. So what is resistivity? Is nothing but, for example guys, imagine I have an iron rod and a copper rod. All right, iron wire and a copper wire. Let's say copper wire and iron wire. Both of them have same 1 meter length and 1 meter square cross-sectional area. Which, does this mean that they will both conduct in the same way? Does this mean that iron and copper are equally good conductors? Definitely not, right? Copper is still a better conductor than iron. How do we decide that? So basically, if I take the same length and same cross-sectional area, how much resistance is offered by that material, that is what is known as resistivity. So resistivity is nothing but the property of the material. So here we know that copper is a better conductor, but iron is not. Why? Because we know that the resistivity of copper is comparatively lesser, resistivity of iron is comparatively more. So this property of the material which decides whether it's a good conductor or bad conductor, that is nothing but resistivity. It is nothing but the obstruction offered to the flow of current of unit length and unit cross-sectional area. That means 1 meter square area and 1 meter length, or 1 centimeter square area or 1 centimeter length, how much resistance is offered by it. So here, when you talk about resistivity, the length and area would remain the same, because we know that if you increase, see, if for example, let's say that I increase the length of copper and then I try to compare it, then it doesn't make sense, isn't it? Because we know that more the length, more the resistance. So here we are trying to keep it, a level playing ground. We try to make sure that, everyone gets equal opportunities, and that's why this is how, that's why you define it as unit length and unit cross-sectional area. So the formula is what, guys? R is equal to rho L by A. So if you take A to the other side and L to the other side, you can also write it as rho is equal to R into A by L. So it gets modified to this. The SI unit of resistivity is ohm meter, because if you look at the SI unit of resistance, that is nothing but ohm. The SI unit of area is meter square, and the SI unit of length is meter. So meter square gets cancelled. So ohm meter is the SI unit of resistivity. All right, it is defined as ohm meter. So these are the four factors that resistance depends on. One is the length, cross-sectional area, temperature, and resistivity. Although temperature is not mentioned in the formula, it does not mean the temperature does not affect it. More the temperature, more would be the resistance, because they gain more energy and they will collide more number of times. So like I told you before, people, so there are few conductors which follow Ohm's law and few which does not follow Ohm's law. So those which follow Ohm's law are called as ohmic conductors, and which do not follow Ohm's law are called as non-ohmic conductors. So conductors which obey Ohm's law are called as ohmic conductors, which do not follow Ohm's law are called as non-ohmic conductors. Here, if you look at the VI graph, it's going to be a straight line. We saw that it's going to be a straight linear curve. Here it can be a curve, it'll be curved, it will not be a straight line. Resistance is constant over here. Resistance can be dynamic in the sense it can be changing. For example, if you talk about LED transistors or diodes and filaments and all that, here the resistance value would also change, and these are non-ohmic conductors because the temperature is also much more higher here. But if you talk about filament and all that, but if you talk about ohmic conductors, you can give the example of copper wire and normal resistors. So these are all ohmic conductors because they actually follow Ohm's law. All right, people. So that said, let's move on to the last couple of topics for today. I believe you have understood everything so far which is being taught. If you have any doubts, let me know in the comment section. I'll try to clear it up as well. Now let's go on to the last three topics, guys, which is nothing but electromotive force or EMF, terminal voltage, and internal resistance. What are these basically? See, electromotive force is nothing but, guys, it is nothing but the maximum amount of energy that the battery can supply to the charges. See, the thing is, guys, if you think about a battery, battery's job is to provide energy to the electrons or to the charges so that they can flow through the entire circuit and come back to the negative terminal. This is what is the function of a battery. It does some work, or it does some work by giving energy to the charges so they can flow through the entire conductor. So for example, if I take a simple AAA battery or AA battery, guys, they would have mentioned that the potential difference applied by this or supplied by this is around 1.5 volts. This is what is called as the EMF. So before you actually connect the battery into the circuit, or before you turn on the circuit, the amount of potential difference applied or supplied by this battery, that is what is called as EMF, and it is represented by the letter E. Or they have written it as epsilon, but it's nothing but E. It's nothing but E. So we know that V is equal to W by Q, because work done is equal. It's nothing but potential difference. It's nothing but work done by charge. So you can write it as E is equal to W by Q, where W is nothing but the work done by work done by the battery to push these charges, and Q is nothing but the charge flowing through the conductor. So this is how you define EMF. It is nothing but it is again energy spent per unit charge for taking a positive charge from one point to another. So what is the total energy spent? That is what is called as EMF. In simple words, it is nothing but the potential difference applied, or the battery see, for example, guys, if I take a battery, like I told you before, they would have promised you that it will give you 1.5 volts, but do you actually get 1.5 volts? Not really. So what they promise, what is the actual potential difference applied by the battery before you connect it or before you turn it on, that is what is called as EMF or electromotive force. All right, this is the definition of EMF. Now there are a few factors that it depends on. One is that it depends on the material of the electrode, that is your anode and cathode, because even in a dry cell you have anodes and cathode. So that is what makes up your positive and negative terminal. It also depends on the electrolytic solution used. Like you have probably seen that in certain batteries and all, we have lithium ion, used in some, we use different chemicals. So that type of electrolytic solution that is used, that is also an important factor. The things that EMF does not depend on is the shape of the electron. It does not matter whether it's rod shaped or cone shaped. That is not a factor that it depends on. It does not depend on the distance between the electrons, and it does not depend on the amount of electrolyte as well. All that it depends on is the material and the type, what type of electrolyte is used is all that it depends on. The next topic, guys, is nothing but terminal voltage. What is terminal voltage? Is nothing but see, like I told you before, if let's say that the battery is promising, if the company is promising you that they'll give you the potential difference, the voltage provided by the battery is 1.5 volts, you will not actually get 1.5 volt. You might be getting around, let's say, 1.3 volts, or maybe you might get on 0.9 volts, something around this. Or you'll be getting somewhere between 0.9 to 1.3 volts. So the voltage that you're actually getting when you turn on the switch, the voltage that you're getting, that is what is called as the terminal voltage. Or you can say that terminal voltage can also be defined as the voltage across the terminals of the cells or the battery. If I take a conductor, if I take a simple conductor, this is what is known as terminal voltage. So if I take these 2 points, the voltage across these 2 points, this is what is called as terminal voltage, which is represented by the letter small, the capital V. You can say that it's nothing but capital V. It has nothing but the, so if in case you see this, when the switch is not on, when the circuit is not connected, when the cell is not connected, in that case, terminal voltage will be equal to EMF. But in real scenarios, it is not always going to be the case, because because of internal resistance and all that, you will not actually be getting around 1.5 volts. All right. So if it is represented by the letter capital V, again the formula is W dash by Q, where W dash is nothing but the work done by the battery to carry the charge inside the cell. Inside the cell, what is the work done, and Q is nothing but the charge inside the cell. So this is what is the formula for terminal voltage. Finally, we also have something called as voltage drop. So like I told you, if for example, if the potential difference is supplied by the battery is 1.5 volts, but what you're actually getting is 1.3 volts, then this drop, this difference that you see, this is what is called as voltage drop. So that's around 0.2 volts, right? So this is what is called as voltage drop. It is nothing but the work done to carry a positive charge through the electrolyte inside the cell. See, inside the battery there is an electrolytic solution, right? So the work done, or basically the work done to move from one point to another inside the cell, that is what is called as potential difference. That is what is called as voltage drop. So because of this resistance inside the cell, that is why you're getting this drop, right? So that is what is represented by voltage drop, which is represented by the letter small v. Capital V is terminal voltage, small v is voltage drop, which is equal to W by Q. Small w because it is work done inside the cell, and Q is nothing but the charge the charge through the electrolyte. So that is nothing but voltage drop. All right, people. So these are the important terminologies that you need to remember. One is terminal voltage, the other is EMF or electromotive force, and finally voltage drop. I hope you've understood this. So basically, this is how you define these guys. Now there is a small relationship between EMF and terminal voltage, which is a very important one. So I'm going to quickly take you through that as well. So here, guys, let's say that the work done by the cell outside and inside is capital W. That is a total work done. Inside the cell also there is work done. Outside the cell also there is some work done. That is nothing but capital W, and the charge is nothing but Q. Now let's say that W dash is the work done outside the cell. Alright, so if I have a circuit, let's say a very simple circuit. See, the total work done to move from one point to another, I'm going to call it as W. Alright, capital W is nothing but work done inside the cell. Here also there is some work done. Throughout the cell also throughout the circuit also there is some work done. That is capital W. The work done only outside, I will call it as W dash, with capital W dash, which is nothing but work done outside the cell, and small w is nothing but the work done inside the cell. Alright, so according to law of conservation of energy, that means that the work done should remain same. So I can write as capital W is equal to small W dash plus small w, because the total work done should be equal to work done inside the cell plus the work done outside the cell as well. So we can say that W is equal to W dash plus W. Now we also know that what I'm going to do is, guys, I'm going to divide this entire equation by Q. So when I divide this entire equation by Q is equal to W dash plus W, I'm going to divide this whole equation by Q. When I divide this whole equation by Q, I'll get it as W by Q is equal to W dash by Q plus small wq. Now what does this mean? W by q is nothing but electromotive force, because that is nothing but the EMF. W dash by q, that is nothing but the terminal voltage, which is nothing but capital V, because it is nothing but the work done to move unit charge outside the cell. And small w by q is nothing but, small w is nothing but the work done to move a charge inside the cell, so it is nothing but small v. So EMF is equal to the terminal voltage plus the voltage drop. That is what is written over here. So you can say that, then if you rearrange the equation, we can also say that terminal voltage is equal to EMF minus voltage drop. So what you are actually getting is equal to the total potential difference minus what is the loss. That is what is called as, that is basically what is seen over here. Now, this is what you need to understand when it comes to the relationship between EMF and terminal voltage. But there's another thing that you need to know, guys, which is nothing but the internal resistance of the cell. Like I told you before, there is some work done inside the electrolytic solution also. So when the electrons are moving from one end to another, when the charge is moving from one end to another, the resistance offered by the electrolytic solution, that is the resistance offered by the cell, inside the cell, what is the resistance offered? That is what is called as internal resistance. So if I take a battery, if I take a very simple battery, the resistance inside the cell, that is what is called as internal resistance. External resistance is nothing but the resistance of the circuit. Internal resistance is nothing but the resistance inside the cell. So if you talk about a battery, you can see this is a battery. You can see that this small r is nothing but the internal resistance. So this is the terminal voltage across the battery. What you get? So let's say that this battery promises to provide 1.5 volts, but what you're getting across, because of the internal resistance, is going to be much more lesser. Let's say that's around 1.2 volts. That is what is your terminal voltage. So you'll get it as 1.2 volts over here. So this is the external resistor, that is the internal resistance. Now there is another relationship between EMF, terminal voltage, and internal resistance as well, people. So the relationship is actually quite simple. So total resistance is equal to capital R plus R. So total resistance is what? It is nothing but the total resistance of the entire circuit is R, which is equal to the external resistance. So I'll take it as RT for now. The external resistance is capital R, that is the resistance of the circuit, plus small r, which is nothing but the internal resistance. Now we know that basically we know that resistance is equal to voltage by current, and current is equal to voltage into voltage by resistance. So here, guys, total you can say that total resistance is equal to total EMF of the cell divided by the total current. So that is what they have written over here. And we know that total, this can be written as I is equal to epsilon or E by R, which is nothing but the total voltage divided by that is the EMF divided by the total resistance. And here this total resistance is what? Total resistance RT is what? It is nothing but R plus R. So I can write as I is equal to epsilon by R plus R. So that's how you get this equation. All right. Now here, people, once again, we are going to use our term. We know that terminal voltage is equal to V into I into R, which is nothing but the external resistor R and the external current I, and V is nothing but the external voltage. Small v is nothing but the internal voltage, which is equal to internal current into the internal, so the current flowing through it, and into the internal resistance. So from the equation that we got before, we know that EMF is equal to external, the terminal voltage plus voltage drop, which is voltage drop is equal to what? Epsilon minus or E minus V. This, if you substitute the values over here, so V is equal to what? V is nothing but I into R. And epsilon, as you just saw before, it is nothing but I into R plus R, and this is nothing but I into R, right? It's nothing but I into R. So here, once again, people, if you just substitute the values over here, you can just remove I from this equation. So what you'll get as R is equal to R plus R. R plus R minus R is what you're going to get. So basically, if you rearrange this equation, you will get the equation that you require. All right. So now you've understood what is internal resistance. There is another relationship between internal resistance, EMF, and the terminal voltage as well. So we're going to talk about that as well. It's a very simple derivation, a very simple relationship. So pay attention. You'll easily understand this. Couple of things that you've already studied, the relationship that we've already done in the past. We're going to use that over here as well. So first thing first, people, draw a simple circuit. So if I have a simple circuit, let's say which has a resistor connected to it and there's a cell connected to that, the external resistor, let's say that the external resistance is R. All right, I have a resistor R connected to the circuit. The internal resistance of the cell, let's say it is small r. Now If I want to find the total resistance, I'll just call it as, okay, the total resistance here, the total resistance of the circuit is equal to what? External resistance plus internal resistance. And the total current flowing through the circuit is what? EMF of the cell divided by the total resistance, which is nothing but what? R plus R. And we have already seen in the past that terminal voltage is equal to current into the external resistance, and internal or voltage drop is equal to current into the internal resistance. We have already seen all of these in the past. Now we have also seen one more relationship, that is nothing but EMF of the cell is equal to terminal voltage plus the voltage drop. Now from this equation, guys, we can get the voltage drop. So what is voltage drop is equal to? Voltage drop is equal to EMF minus the terminal voltage. Now what we're going to do over here, people, is that we are going to substitute the values in this equation. So from this equation, what I'm going to do is I'll basically substitute for V. All right, now what is V equal to? We know that V is equal to IR is the basic formula that we have, which is nothing but the total current into the internal resistance. So R is equal to what? R is equal to V by I, that is the voltage drop divided by the total current flowing through the circuit. So I'll just substitute in place of V, I'll just substitute this in place of, what I'm going to do is I'll just substitute this equation over here. All right, I have this equation that is nothing but R is equal to V by I, because I have to find out the relationship between the terminal or the internal resistance and EMF and terminal voltage. So in place of R, in place of V, we'll substitute E minus V, which is nothing but the EMF minus the terminal voltage. So R is equal to E minus V divided by I. Now the total current flowing through the circuit is what? Is nothing but terminal voltage divided by the external resistance. All right, terminal voltage minus the current flowing through the circuit. If we talk about the current flowing through the circuit, that is nothing but the terminal voltage divided by the resistance. So I'll substitute that also in this equation now. So R is equal to EMF minus the terminal voltage whole divided by V by R. Now from this equation, guys, R will go to the numerator. So R is equal to E minus V whole divided by V into R is what you have. Now here, guys, I can write this as E by V minus V by V into R, right? So here I'll basically get this as what? E by V minus 1 into R. This is how, or this is the relationship that you see, guys, between terminal voltage, your internal resistance, and your EMF of a particular cell. So this is the relationship. It's a very simple relationship. I hope you've understood this. So once again, just a quick recap, people. So we know that the total resistance is equal to R plus R. The current flowing through the circuit is nothing but EMF divided by the total resistance. And we also know that V is equal to basically IR. And basically we are using this equation also later. That is I is equal to V by R is what we're using later on as well. And we also know that EMF is equal to terminal voltage plus internal resistance. So internal resistance is equal to EMF minus terminal voltage, and we know that internal resistance is equal to V by R, that is voltage drop divided by the current. In place of V, we'll substitute the value that is EMF minus the terminal voltage, and then we'll substitute for I as well, which is nothing but V by R, which is nothing but voltage by the resistance, the terminal voltage by resistance. So we'll put that also in the equation, and then simplify that further on, and you will basically arrive at this particular equation. This is the relationship between EMF, terminal voltage, and internal resistance. Now to talk about the factors affecting internal resistance, people, it depends on the surface area of the electrodes. So the more the surface of the area of the electrodes, the internal resistance would be much more lesser. Basically it's resistance, so more the area, lesser would be the resistance. Distance between the electrodes is also another factor. More the distance, more would be the resistance, just like what we learned before. For resistance also it was the same thing. Here also it's pretty much the same thing. The nature and concentration of the electrolyte, that is the type, the property of the type of an electrolyte used, that is also a deciding factor. Some of them might offer more resistance, some of them might offer lesser resistance, and finally the temperature of the electrolyte as well, because more the temperature, more would be the internal resistance in that particular cell. Alright guys, so this is the electricity one shot part number 1. The part 2 would be coming up later on, but I hope it's all understood, people. I hope the whole ideology is clear. These are some of the topics were actually very simple, very straightforward. Some topics are new to you guys, like electromotive force, that is EMF, and terminal voltage and stuff like that, but I hope it's clear now. If there's any doubts, any confusions in general, please let me know in the comment section and I will try to clear it up. So just a quick recap once again, just quick recap people about this. EMF is nothing but the voltage that the battery is providing. The maximum voltage that the battery can provide is what is called as the EMF. The maximum amount of energy that a battery can supply is what is called as an EMF. That is nothing but before you turn on the switch or the batteries, the value of the battery that you get. Like for example, if I talk about a AA battery, it tells you that the voltage is 1.5 volts. That is the EMF of the cell. That is what the company is telling that they'll provide. But because of certain factors, you're not getting so much. What you actually get is the terminal voltage. So when you connect that battery to the cell or to the circuit, the voltage across the terminals, the voltage across the battery, that voltage is what is called as the terminal voltage. Generally, what we do is that we measure it at two ends. So this would give you the terminal voltage, which basically would be a little lesser than what the company had promised. So that's about, let's say, about 1.5 what was offered, but 1.3 is what you're getting. And finally, when you talk about internal, the voltage drop is nothing but the difference in the EMF and the terminal voltage is what is known as a voltage drop. All right, and this is the relationship between them. Voltage EMF is equal to terminal voltage plus the voltage drop. Alright guys, I hope it's clear now. So that's it people, that is all for today. And yes, if you guys want to showcase your talent, we are always coming up with opportunities for you guys. So we have Vedantu's Got Talent season number 2 coming up. So if you guys are interested, whoever you are, singer, dancer, poet, a comedian, if you want to showcase your talent, this is an amazing platform for you guys to show the world what you're truly made of. And yes guys, we are always here for you with respect to your term 2 preparations as well. So if you guys need more help from our side with respect to your preparations for your board examinations, we are always here with you guys. We're always here to support you. So you can always enroll into our sessions and learn more and gain more from these sessions as well, because we only do one shot series on YouTube, but on the regular platform we'll be doing everything else. Or you'll be having regular sessions. You'll have total doubt support as well. 24/7 you'll have doubt supports. You can you'll have access to all the unlimited amazing questions and answers that that is required for your preparations, and you'll also get a detailed revision plan which will help you to cope up with your exam and prepare in the right manner. Not only that guys, you're getting lots of stuff over here. You're actually we ensure that you're enjoying the process of learning. So we tend to start off the session with a riddle or with a code to give you that nudge that you require, and we always try to keep it interactive. We have thumbs up, thumbs down, we have hotspots, we have quizzes in every session, we have leaderboards, fastest fingers list, stars, we have drum rolls, we have class teachers, which you can even get yourself unmuted in the class, which is not an option in YouTube, because here whatever happens is through typing. But over there guys, you can even get yourself unmuted and you can talk to the teacher and get your doubts cleared at any point in time you want. And to give you a statistics guys, so like I told you, you also have someone called as a class teacher who's available in the class to help you with your doubts. So in this particular session, about 88 doubts were asked, and you can see that about 88 doubts were actually resolved in that particular class as well. So all of the doubts that were asked were cleared in the class, and you can download all of the notes, so you don't ever have to worry about notes or taking down running notes and all that, because everything is downloadable and you can watch it, read it whenever you want. And you also have stress relief sessions, you have yogas, we have lots and lots of amazing content, some amazing stuff always that is going on over here. So we'll always be there for you guys to help you with your preparations, right? So how do you enroll in the course? It's very simple. All you have to go is go to the description of the video. This is for CBSE. Now if you guys want more detailed description or understanding of the concepts, I have done the whole chapter of electricity for CPC students, and it's very similar to ICSE as well. So if you guys need more help, I've taken up videos on that as well, so you can check it out of all the topics except for EMF, terminal voltage, and all of that. Everything else, voltage, current, resistance, I've done separate videos on that, so you can check that out as well. So what if you do is, guys, go to CBSE Crash Course, click on this link. This link will help you to enroll into the course. Unfortunately, my internet is always there for me when it comes to, it never lets me down. Never ever lets me down. So anyways, you have to go to CBS ICSE Crash Course, people. So once you go to ICSE Crash Course, so change that, go to ICSE Crash Course, and you'll be getting the whole syllabus over here, the entire all physics, mathematics, everything together. You're getting an amazing deal right now, people. It's about for 8,775 rupees, and that is about 20% off. And if you guys don't want to pay 8,775 rupees, that is for the entire course until the end of your examination, is how much you're paying. Is how much you're paying for this. Now, if in case you don't want to do that, 8,000 is a lot of money. You feel like you're new and you want to try it out first, you can even enroll into the 30-day program. The 30-day program is just 1,170 rupees for all the subjects that I mentioned, science as well as mathematics, for just 1,170 rupees for the entire month. So which means that for the whole month of Feb and the first couple of weeks of March as well, you'll be paying about 1,170 rupees, where you'll be finishing about 60 to 70% of your syllabus. So that it's better than doing nothing. That's what I would say. And if you are not, if you are like 8,000 is a lot of money, you can actually enroll into the, it's not a 15-day trial, it's a 30-day trial. If you use my coupon code AME Pro, you'll be extending it to 30 days, and you'll also be getting a really good deal on that as well. So all of it is in your hands. Now let's get into some questions, check our knowledge, see if you have understood the syllabus or not, how understood what the concept was taught today. And yes, let me know if you have any doubts in the comment section. I'll be looking out for your feedbacks, right? So here's the first one. Resistance offered by a conductor does not depend on dash of the conductor. Resistance does not depend on which of these factors? Length, area of cross section, temperature, or surface area. Which of this doesn't? Area of resistance. The resistance in general does not depend on length, area of cross section, temperature, or surface area. I'll start the quiz, guys. I'll tell you the answer in 5 seconds. If you need more time, pause the video and try to figure it out. I'll answer in 5, 4, 3, 2, 1. It is actually the surface area, people. It depends on the area of cross section, but it does not depend on the surface area. It does not depend on the surface area, like how much area is exposed to the air and all. It does not depend on that. It depends on the cross sectional area. So if I take a wire and cut it in half, basically it'll look like a circle from the front, right? It'll look like a 2D circle. So it depends on the cross sectional area. It depends on the thickness of the wire, but it does not depend on the surface area. Next one. Which of the following is the purpose of connecting a battery to an electric circuit? Why do you connect a battery to it? To maintain the resistance across the conductor, to vary the resistance across the conductor, to maintain the constant potential difference across the conductor, to maintain varying potential difference across the conductor. Why do we connect a battery? Like, what is the reason that you have to connect a battery to a circuit? Why can't you just do it as it is? Like, why do we have to connect a battery? Answer it, people. I'll let you know the answer in 10 seconds. You guys figure it out. Pause the video if you need more time, but I'll give you the answer in 5, 4, 3, 2, 1. It is option number not D, C. For all those who told it's option number D, I'm pretty sure some of you guys would have gone with option number D. That is not the right answer, people, because battery provides a constant potential difference. It is not a varying potential difference. It's a constant potential difference. For example, when I connect a battery of 1.5 volts, I am giving a potential difference of 1.5 volt. It's not that it's 1.5 volt 1 second and then it's 0.9 volt next second. No, it's 1.5 volt constant. So it provides a constant potential difference so that current can flow through the circuit. Next one. If the area of cross section of a conductor is doubled, then what will happen to its resistance? Will that also be doubled? Will it remain the same? Will it be halved or becomes 1/4? Now this is a very interesting question. So I believe you already know the formula, people. Resistance is equal to resistivity into length of a conductor divided by the area of cross section. Now here, since the area is actually halved, so what will happen to your resistance? It's doubled, right? Sorry, cross section is doubled. Sorry for that. So your area of cross section is doubled. Area of cross section is doubled. So if your area of cross section is doubled, then what will happen to the resistance? The new resistance, I'll call it as R dash. So new resistance is 1/2 of R. So this is nothing but what? This can be written as 1/2 is into rho into L by A, right? So rho into L by is nothing but R. So I can say that it's nothing but half of the original resistance. So option C would be the right answer for this question. So that's it, people, and thank you for joining us. Thank you for being a part of this family. If you guys enjoyed the session, let me know in the comment section. Hit the like button, subscribe to the channel, do everything that is needed, and yes, check out. If you guys want to reach out to me, you can always reach out to me at anoop.manoharan@vedantu.com. Thank you for spending your time with me, guys. Have a wonderful day ahead. All the best for your exam results. I heard that your term 1 examinations are coming out soon, so good luck for that, and also good luck for your term 2 preparations. I hope that this video helped you people with your preparations, and if you have anything that you need more information on, always let me know. I'm always open to suggestions. I'm always open to your feedbacks, so let me know how we can make it better and help you guys in a better manner. All right, guys, thank you for joining. Have a wonderful day ahead. Adios for now. Take care, stay safe, and catch you guys later. Peace out. Bye bye.